4 problems on there. Figure if we can work those 4 by the end of the day. So what I'm doing is I'm basically, wait a minute. It didn't save. Yeah, it did. There we go. So these are, so there's a, that's where I left us at. And what I'm doing is I'm working other problems. And so I'm going to kind of work problems in theirs and then a different one in yours for about a week. And then so that I'll cover a lot of problems, but they all look about the same. So I work those problems. And there's the video there. You could watch it in high speed, actually. So I'm going to do the same thing and work this set. And then that means Friday, I'll start 50. Yeah, I'm sure it, I hope it works right. So it says a 2-bound. Okay, so before I do any of these, let me make sure I got the pin the way I want it. Okay. So all of these energies, I always start the same way. mgh1 plus 1/2 k delta squared. I know there's no spring, but I just write the equation just blindly. Plus,
well, is it just like basically one equation?
Yeah, just reapplied to all the different. Yeah. So to me, if I always write the same equation, now what he does in the book, and this is the part that, you know, so in the book, he has this term T, he has a term V, he has U from 1 to 2. And if you look at all of these and look at those equations all together, you'll realize all of them in all single cases, this covers all of that. And that's why I come back to this, is it covers everything. So this way I don't have to remember, well, okay, what was T, what was V, what was U, all that sort of stuff. This way I remember I have potential energy here, kinetic there. I may lose or gain some energy due to friction or somebody pushing on a box or whatever. Then I have potential energy here, and then I have kinetic there. And so to me, I just do it that way because it, sort of straightforward and it covers all cases. So I come in here. Okay, so now I started addressing this, okay? First thing, I got to figure out my H's. So I'm just going to take this to be my Z or H, whatever you want to call it. Different books will call it Z. So this is the height you move a box up or down. So if I do that, then that means H1 is equal to 0. H2 is equal to, wait a minute, determine the velocity of the box and when the box is at C and at B. Okay, so let's do state 2 equal to B first. And then we'll say this will be state 3 is equal to C. So I could redo this equation another case. So H2 would equal to 5 foot. H3 has got to equal to 10 foot. So I'm basically defining 2 of these end states. Okay, since, yeah, and this is going to go up here to this one. So this will be 10 foot, that'll be 5 foot. Now I'm going to come back and say, well, V1 is equal to, he told me, 30 feet per second. V2, I don't know. V3, I don't know. There is no springs. And is it smooth? It's smooth, so there's none of that. So that tells you that the only thing that happens is the kinetic energy turns into potential by sliding up the hill. And so what I get is mgh1 plus 1/2 mv1 squared is equal to mgh2 plus 1/2 mv2 squared, where 2 is equal to B. Yeah, that's right. And then state 3 is C. So I get, since there wasn't any loss of energy all along the way, I can do that. Okay, so now I'll address each one. Oh, well, that's easy. That's 0. So I get 0 plus 1/2. And the thing is, oh, it's 2 pounds, 32.2. So that's how many slugs it is. Going 30 feet per second. So the thing has that initial energy. So that energy is,
That's what I'm saying, is you don't have to put it in 2 over 3.
yeah, you don't, but should I do that? Should I knock it out? But yeah, then it won't. Yeah. Well, you know what? Since I'm shooting for that, I think let's go ahead and do that and make it easy. I think you're right. Let's just make it easy. I'll just go ahead and cross out that. No. So I'll say that, and then, wait a minute. Actually, well, it will show up. Well, it's not a bad complication. So I got this potential, I mean, the kinetic energy right there without the mass. Then I got to have GH2. Well, G is 32.2. And if I was putting the mass back, the mg would be just that 2 pounds. H, this case is 5 plus 1/2 V2 squared. But it's also equal to 32.2. In this case, it's 10. 1/2 V3 squared. So now I've got 2 possible things to worry about. First, let me worry about what's on the left side here. If I pull up MATLAB, let's do a clear 30 squared divided by 2, 450. I got 450 is equal to 5 times 32.2 and then 10 times 32.2. This 161. Whoa. 161 plus 1/2 V2 squared is equal to, okay, but it's also 322 plus 1/2 V3 squared. So there's more, as you get higher, this number overruns it. And so even at this point, both these numbers are smaller than that 450. So what I'll do is get V2 equals to 450 minus 161, but I don't have enough room. So then, well, times 2 and then the square root. But I'll also get V3 is equal to the square root 2 times 450 minus 322. I don't know what those numbers are. Okay, square root of 2 times 450 minus 161. 24. I'll just say it's 24. And then I'll say V3 is around, you got it, 16. Now I think did he ask for something more, or is that all he asked for? Velocity of the box and the normal force acting on the ramp when the box is located at B and at C. Okay, so let's do B first. B, the box sits like this. It's flying along in this direction, V. It's got a mass. I shouldn't have put that arrow on there. Here, I'll do it like this. How about like that? So it's V, it's 24. It's got a normal force there. So here's your normal. So what you do, sum of the forces, here I'll say the normal force. And this is, was it 2 pounds? 2 pounds. Sum of the forces in the normal direction, how about like that, equals to mass V squared over rho. Well, rho was 5, right? Okay, so on the left, all you get is the normal force. On the right, you get the 2 pounds, 32.2 The speed is 24 squared, and then the R is 5. So you should get, maybe you should get, hopefully you should get 2 divided by 32.2 times 24 squared divided by 5. 7.15. 7.15 pounds. That free body diagram looks different than when it's at the top. When it's at the top, this is the normal force. Ooh, that looks funny. This is the weight, 2 pounds. Speed is going this way. And that's it. So if you look at that, sum of the forces in the normal direction equals to mass, v squared over rho. Go ahead and stick them in. 2 over 32.2, that's the number of slugs. 16 squared divided by 5, because it's still 5. On the left, since that's the positive normal direction, you get 2 minus, 2 plus n. Okay, and this number, whatever that number is, or I can just do this. N is equal to 2 divided by 32.2, 16. That's supposed to be squared. Squared over 5 minus 2 pounds. 1.18, okay. Okay, so let's shrink it down and let's check our answers. However, I think I might have used the wrong edition of the book. I'm in the 12th edition. Well, it's too late now. I had the 13th up and I was looking at the 12th. It doesn't matter. They're all the same thing. Okay, so I don't know what problem that was. So it might be a different problem in the... Why did I do that? I don't know why I did that. There it is. So it's 1422 on page 204. Okay, 14, 22. Okay, so we got all that right. Yeah, that's right, because that was one of the numbers. Yep, 7.18. Okay, so we got it. Okay, so now what was it, 204? 204 takes us back to there. Okay. What was the other problem? I think I did that box next. Did I? Okay, go down one, the box. Yeah, I did it because it had a coefficient of friction. This one should be fairly quick. The crate has a mass of 100 kilograms. It's subject to the action of the two forces. If it's originally at rest, determine the distance it slides in order to attain a speed of 6 meters per second. Coefficient of friction is that. First thing I'm going to do is I'm going to find out. I'm going to just use this box with the, as the free body diagram. He did a good job on the box. Uh-oh. What happened? What did he do? I don't know. Oh, I did. My knee hit that DVD button. I thought I broke something. I noticed I had a happy look there. Yeah, there you go. Okay, some forces in the y direction equals 0 because it's not moving up or down. So, did the fan change? It's like the fan changed.
I didn't notice it.
Oh, okay. Okay. Okay, so I got this. I'm going to make that be positive. So I got n plus that 1,000, but I got 3/5 of it. So I'll just write down 3/5 of 1,000. I'll figure that out in a minute. Oh, geez, he's got a 30-degree thing. So then he's got minus 800 times, what is that? Nah, we'll just keep it that way because then that way we can look at the answer in the back of the book, you know. Take that 800 sine 30, that's nothing but 400 minus, okay, 500, that should be 600, right? What?
So it's a negative 40, right? Negative 800 side.
No, because he moved the N over to the other side.
Am I seeing that wrong? Okay, let me make sure I got that.
That's correct.
Oh,
Move your
oh,
to the other side,
oh.
and it's going the opposite direction.
Yeah, I forgot something else too. I was like, wait, 100 kilograms. Okay. So that is an opposite. So I got to put that 9810. Wait a minute. One digit, two digit. Wait, one. Yeah. Yeah. Okay, now. Okay, so to move that over. Oh, shoot. I got to put a. Okay, 981. Oh. You think, is that the right answer? 781 is the total? Okay, all right, yeah. Okay, so I got that, and this is, okay, so the force due to friction is equal to 7, yeah, what is that? It's not 14, it's 15.62. Okay. Oh, is it 156.2? Really? Okay. Yeah, I got my digit in the wrong place. Okay. Yeah. Okay, now I'm in here doing the sum of the forces. What am I doing sum of the forces? I don't want to do sum of the forces. I want to do the 1/2 m. I'm not even going to write the spring if y'all are fine with that. Yeah. Oh, I don't even need to do the MGH, do I? Yeah. Okay. However, what there is, F dot D equals to 1/2 mv2. What did he want to know? Oh, he wanted to know, he wants to have that 6 meters per second. Yeah. So, okay, it started originally at rest. Woo, that makes it easy. I was kept thinking, oh man. Okay, so now I've got all these F dot Ds. Actually, I got 3 of them. I got this one, I got that one, and I got that one. So actually, I got 3 of these things. So equal to 1/2. What is the M of this thing? 100. And this thing is 6 squared. So let's see, it's 36. 36 and half of 36, 18. It's 1800. Is that right? Okay. All right. So here's the problem. Okay. So this thing is going to move to the right a certain distance, which we don't know. However, here, let me see if I can. I wonder if I could do this. Let's try something. Take that, shrink it, move it up a little bit so I'll have a little bit more space down here. There we go. Okay, so I got 1800. Well, the first one, let me count for each one of them. I'll start labeling this one 1, this one 2, and this one 3. And these are all my forces. So my first one is 800, but the one that's going in the direction of D is the cosine part. Cosine of 30, because that's going in the direction of D, If you dot those two vectors, it's going to be plus, but it's also going to be d times that. So that, in fact, is for that first one. The second one, distance, I'm doing f dot d, so I'll do the distance first. The f in that direction is the 4/5. 4/5 of 1,000. I think that's 800. I think that's the second one. So this one and this one give energy to the system. The next one takes it away. And it's taking it away because the F is going in the reverse direction of the distance. We figured that out as 156.2, and it's a distance D. So this sucks energy out of the system due to friction. That's the friction loss. So now I just got to find each one of these terms. Okay, so I come in here and I do 800 times cosine degree of 30 plus 4 divided by 5 times 1,000. What? That's 156.2. Ugh. Okay. Yeah. What was it again? 13. Okay. Okay, so let's see. Let's do it this way. Slide all this junk over here. 1,800 divided by that. 1.35 feet. Meters. Okay. So that one's kind of beneficial because it shows, it kind of highlights this thing. What happened? Okay, that's weird. Okay, now I don't know what happened. Where did it go? Okay, well, now I don't want to. Okay. I was just going to try to get over here and do this and say this problem highlighted that thing. Now let's see how off or wrong I am there. Okay, this time it's 1426. Still on page 204. 1426. 14 here. I better get rid of this. Better get rid of that one. 1426. Close. Oh, 1.35 meters. Is that what I got? Yep, that's it. So all that to get that. Let's see. What's the next problem? Oh, where is it at? Where? Oh, right here. That one? No, not that one. Really? Did I do one in the? Wait a minute. No, that's not. Wait, is that the one?
What'd you think of it?
He's trying to get off easy on this.
Oh, okay. You got me confused. I'm like, that's not friction or anything. That's a. Well, here, let's do this other one first. Where? Okay, wait a minute. What? Okay. Here we go. Yeah, they confused me. Okay, so do I want to do this one next or the next one? I don't know. You know what? Maybe I'll do this one and then do the next one, and then I may call it a day after this one. Instead of doing 4 today, I'll do 3. How about that? Well, I don't know how many I do most any day. Yeah, there you go. So this says if the coefficient of friction is between the 100 kilogram crate, oops, here, 100 kilogram, that's 981 newtons. Is that right? I hope that's 981. Okay, so 981 newtons. That means this one and this one are equal because it's 45. So this would be 981 divided by square root of 2. And that'd be 981. Same thing. 693.7. 693.7. Since the coefficient of friction is that, then it must be this friction is 693.7 times 0.25. What's that number? Okay, so that's the force due to friction that's slowing this thing down. Determine the speed of the crate at the instant the compression of the spring is that. Initially, the spring is unstretched and the crate is at rest. Okay. So here I'm just going to do all of them. MGH1 plus 1/2 K, that's not a K, K delta 1 squared plus 1/2 M V squared, this is 1, plus all the F dot Ds, which I guess I should put a summation on that. But there's only one in this case. Okay, wait a minute. Okay, then MGH2 plus 1/2 K delta 2 squared plus 1/2 M V2 squared. Okay. He says this is 10 meters. He says I'm going this, so this is actually, this distance is 11.5 meters. So if that's the case, and I look at the distance between here and here, that has to be 11.5 divided by square root of 2 because it's 45 degrees. And that is 8.13. Okay, so I'm going to take my datum to be right there. So that's the case, then H1 will equal to, whoops, H1 is at the top, 2 is at the bottom. So H1 is 8.13, H2 is equal to 0. That gives me my potential energy difference. So now I've got 100 kilogram crate, 9.81, 8.13, plus no kinetic energy, no potential energy, no kinetic energy. Now what happens to me is I scrub off some energy as I go down. Force of friction times the distance, or 11.5, because I'm scrubbing off that energy, which actually the force of friction we already figured out, or you did, 173.4 equals to, that's 0. This has some potential energy, which he says the spring is compressed a certain amount, 1/2 K. Okay, now this I got to be careful of. That's kilonewtons, and these are newtons. So this has to be 2,000 delta. Delta, he said, is 1.5 squared plus 1/2. The mass of this thing's still 100, And there's their speed. Wow, I hope this thing works out. So 100 times 9.81 times 8.13 gives me 7975. 7975.53 minus. Okay, I'm a little scared. 173.4 times 11.5, 199, 4.1 equals 2. And all that spring energy here, 1.5 squared times 2,000 about 2, 2250 with no digits plus 50 times v squared, and that's because of that. So now, here, scratch down so I can move down the page. That's what you get by moving all that. 8.64. Okay. Okay. Let's okay. Now it was okay. Did I leave the number with it? 1434. 34. Okay, there you go. So I don't know. Do y'all want to do another one? Y'all want to do that last one or?
Unless the last one commits.
Nah. Oh man.
That midterm's not nice, dude. I don't know what you really.
Oh, it was okay. It's all right. Here. It's not bad. It's okay.
It's not sharp teeth. We'll survive.
It's okay.
SPM is 2.
It's a beautiful picture. Look at it. And I'm just really.
That picture looks beautiful.
Let's look at this one. Look at how nice that picture looks. That's pretty cool. Oh yeah, y'all sign your sign. Did y'all sign already? That's a good picture. That looks like the other picture, doesn't it? Yeah. So do you do either one of you like put it in CAD? Because there's things you can do to put it in CAD